Welcome back from the break, guys. Thank you so much for joining us. As always, we've got a WhatsApp question, so we're going to have a look at that.
How do you answer electrostatic questions when you're asked what happens to the force if you change the charge and distance between charges?
Right, it's a wonderful question that has a lot to do with the basics of electrostatics. Now, let's quickly look at some of the key things that we need to consider as far as, because this has to do with the Coulomb's law. It's important for us to identify the concept involved in the question. So once it talks about the forces, and the distance of the charges, we need to classify that question under a particular concept. So we appreciate the fact that this is about the Coulomb's law, essentially, right? And then what are some of the most important things in response to this very generic question is that you need not to forget that when we talk about Coulomb's law, we are talking about the electrostatic force. So the electrostatic force is a vector, right? So direction needs to be taken into account always. And remember, every force is applied on a particle or an object by another, okay? So the direction becomes very crucial. Now, also make sure that you learn the Coulomb's law. We have mentioned the importance of the examination guidelines. So in the formula sheet, it will be written F is equals to K, Q1, Q2 over R squared. So the mathematical equation captures, even the relationship that exists between the product of the charges as well as the electrostatic force, as well as the square of the distance between those charges and the electrostatic force, right? So the key words, directly proportional, inversely proportional, but do not forget that this is about the square of the distance between the charges. But also, there is a thin line between the Coulomb's law and the universal gravitation. Now, in what way? The very same skills that in response to this question to say what happens to the force when the charges are doubled or whatever changes are made onto the charges as well as the distance, we need to recognize that this is the very same skill. We would apply it with the universal gravitation law. But however, the most important thing that the examiner will penalize if you do not include as far as the universal gravitation is that we talk about the distance, the square of the distance between the centers. Well, for particles which are actually minute, so we can even ignore the radius or the diameter. So, but as far as the universal gravitation, the distance, the square of the distance is actually between the centers. All right, okay? Now, the understanding also of the field is very important because in an electric field, another charge will experience an electrostatic force. So while we speak about the electric field, we are also talking about forces. So we are not running away from the vectors once again. Hence we said as long as there are forces and vectors, direction becomes a very key component of that. Okay? So understand that a field is a region in space. Okay, grade 12, you need to distinguish between electric field at a point and electric field. So a region in space is just a field, okay? But if we talk about electric field in strength, we're talking about the force that will be experienced per unit positive charge. So force, okay, per unit positive charge, right? Per unit positive charge. So if we talk of a unit positive charge, we are actually talking about a test charge, which is actually the 1 coulomb of charge, which is positive. All right, okay? Right, so that's the unit positive charge, which is, so even the formula, F E is equals to F over Q. This is given in the data sheet. This is actually the definition in terms of the magnitude of the force experienced by a test charge in a field, okay? But in terms of calculation, we'll talk about a charge Q that creates the field, okay? Now, the distance from the surface of that charge which creates the field and we square it is the one that we actually consider as far as electric field strength. So sometimes we'll refer to it as electric field strength or electric field at a point. So these are some of the, the general stuff that we need to polish up. But also in grade 10, we looked at electric field patterns, in terms of magnets in grade 10. And then in grade 11, we also looked at point charges in space. So when we talk about a point charge, then we know that around that point charge, what exists is actually an electric field, and we use electric field lines. So 3-mark questions are usually asked as far as electric fields at a point. So in some cases, you'd consider the field between 2 point charges, either like or opposite charges. So those are some of the legal things. So in the examination guidelines, you'd have your checklist to say, okay, do I still remember this? If not, what do I need to do about it? Let me revisit and consolidate that as well. All right. And then that's a brilliant question that was asked. But here's another typical example of a question. It says, consider the charges X, Y, and Z with the same magnitude. So these are identical charges in a true sense. This word will be used quite often. Identical, meaning that it could be identical spheres, meaning they have the same shape, size, but necessarily they don't carry the same charge. They may carry the same charge or they may not. But if they're saying these are identical charges, it means the magnitude of the charge of X equals to that of Y, equals to that of Z. The other ones are positive, which is the X and Z, while Y is negative. Now, let's look at the issue of the forces as an example. It says charge X exerts a force F on charge Y. Now, if you look at X and Y, they are at a distance R. So we have recognized that the concept involved in this question is actually the Coulomb's law, which says F is equals to K, QX, QY over R squared. So this is F. This is what is on the right-hand side actually represents F. All right? Now, calculate the magnitude and direction of the force that Z exerts on Y. Now, what's the difference between between Y and Z is that the distance has been doubled, but the magnitude of the charges is the same. Okay? For never mind, Y and Z will experience a force of attraction just like X and Y because these are typically opposite charges. Now, if we double the distance, what will happen? Then it says this is equals to K, Q, Y, QZ over 2R. Now, it's the square of 2R. That was the catch. It's the square of 2R. So if we double 2R, this will be like 1 over 4 K, Q, Y, QZ over R squared. So if that represents F, it means now the new force would actually be a quarter of F. So similarly, that's what you'd even do as far as the masses in universal gravitation law is concerned. Okay, right. And then it goes on further to say, find the force that charge Z exerts on charge Y in terms of F. Okay, so if we double the distance, because we know that the electrostatic force is actually inversely proportional to the square of the distance. It means then, from the calculations that we've done on the previous slide, we know that the new force, the charge by Y on Z, okay, charge by Y on Z, okay, is equals to a quarter of the original charge. So, because we have doubled the distance, okay? All right. And then, as far as electric fields is concerned, also vectors are heavily involved because we're saying that electric field at a point is the force experienced per unit positive charge. Take note of the small letter Q. It's not the big charge that creates the field. That's actually the test charge. This is a unit positive charge, okay? That's our unit positive charge, okay? Which is the +1 Coulomb. Take note of that. So in the definition of electric field at a point, you need to clearly state that this is the force experienced by a unit positive charge, which is why the SI unit is then in Newton per Coulomb. So if we talk about per Coulomb, we're talking about a 1 Coulomb of charge. Okay? So we also need to be able to determine the electric field strength at Z if the charge on Q is doubled. Okay, now, if Z creates, if Q is the charge that creates the field. So E is equals to K Q over R squared. Now, you'd realize that we even talk about the square of the distance between the point and the surface that creates the surface of the charge that creates the field. Okay, so you square the distance, so it's inversely proportional to the square of the distance, while E still remains directly proportional to the charge. So if we double the charge that creates the field, E will also be doubled. If we double the distance, remember, it's about the square of the distance. It will be 4 times as big. If we have the distance, it will be 4 times as big. So we use more or less a similar approach, right? Now, just to use a specific example in terms of the layout of that question. So here is Q, the charge that creates the field. Okay. X is a point, so it's very important. X, that's where we place at X. That's where we place the test charge, okay? Now, if Q, say for argument's sake, is positive, all right? If Q is positive and then we place a test charge at X, obviously Q exerts a force on the test charge away from Q, right? Now, if we place the test charge, let's say, at Z, okay? Obviously, the field strength is stronger at Z compared to Y. One of the things that we also mentioned in grade 11 is that the electric field line density is an indication of the strength of the field at that particular point. Because this is a positive charge that creates the field, the direction of the field is away. So that's another thing that we also need to remember. So as a result, if we place the test charge at a shorter distance, the field is stronger. Even the density of the electric field lines is indicative of that. So if we say, for argument's sake, we double the charge, then if E is equals to K, Q, let's say we double the charge, okay? Now it becomes 2Q. That's the mathematical language. And let's say maybe this distance is a quarter of what it was. Then over 1R over 4 squared, okay? Now, if we do the math, you'd realize that we've got 2KQ over R squared over 16, okay? So this is as good as saying 2KQ over R squared times 16. This is actually 2 times 16, which is 32 E. So if we double the magnitude of the charge Q and put it at a distance that is actually a quarter the original one, which was at X. So this field is 32 times as stronger at point Z than at X. Right, very, very important, concept there. Okay, but now the other, questions may be based on electric field at a point in terms of the net. Sometimes it can be net electrostatic force at a point due to more than one charge in space. So the diagram below shows the charges positioned relative to B. The diagram shows 3 charges that are placed at a distance from each other in a straight line. So these are collinear. Now, if, for argument's sake, we talk about point B, okay, and then we're saying at point B, we place a test charge. Okay, the test charge is always positive, remember, because that's a unit positive charge. Now, the force that it experiences due to this charge, let's call this charge Q2, let's call that Q1. So as a result, the force exerted by Q2 on the test charge at B is actually towards so this is E due to Q2, okay, right? Now, if Q1 is positive, it will repel the test charge away from it. And then this is E due to Q1. So the vector nature of these quantities, your electrostatic force, your electric field at a point, is what we want to emphasize in as far as possible. Okay? Now, having said that, it's also important for us to, in closing, to look at, the overall, tips as far as preparing for the exam is concerned. Remember, the exam guideline, I think we've mentioned this one too many times. Make use of the data sheet. This is always provided. Ensure that the conversion of units is covered, the direction dealing with vectors. And make sure, because this is physics, make sure that you interpret your answer. Due to time constraints, we can go on and on, but these are just examples, of some of the things that you need to revisit. For now, over to you, Lonnie.
Thank you, Themba, and Matrix, thank you so much for joining us and for engaging online. Don't forget to check out the schedules on www.wazamatrix.co.za so you can see when the next revision show will be playing. A big congratulations to all of the competition winners who will be announced straight after the show on the Facebook page. But for now, from me, Looney, Nicolene, as well as Themba, it's thank you and goodbye.